Hello everybody, welcome to this webinar on microanalysis with high spectral resolution, the power of QUANTAX WDS for SEM by Bruker. My name is Max Bugler, I'm a microXRF applications specialist at Bruker Nanoanalytics in Berlin. I'll be the host for this session today. Before we start, let me give you some housekeeping details. You should at this time be seeing the introductory slide on your screen. This webinar is interactive. You can ask questions at any time during the presentation by entering your question in the according box on the right-hand side of your screen and sending them to us. The presentations will last about 30 minutes. After the presentations, I'll present your questions to the speakers. If we are not able to get to your question during this live event, we will follow up with you by email. This webinar is also being recorded and will be available as on-demand version very soon. With this, let me go ahead and introduce our speakers of today. We have first Dr. Jörg Silbermann. Jörg studied chemistry at the Technical University here in Berlin, where he also acquired his PhD in the field of numerical statistical physics. He joined Bruker in 2011 as a product manager for WDS. Our second speaker today will be Dr. Michael Abrates. Michael studied geology at the universities of Kiel and Göttingen, where he also acquired his PhD. During his academic career, he focused on analytical geochemistry using mass spectrometers and microprobes to analyze rocks and their minerals. Michael built up and managed a microprobe lab at the University of Jena before he joined Bruker as a senior application scientist for WDS in the fall of 2015. Now let's get started. Jörg, please go ahead.
Yeah, thanks for the kind introduction, Max, and welcome to everybody also from my side. So the following presentation is basically divided into two parts. In the first part, I will give a short introduction to the QUANTAX WDS system and provide some more details about the spectrometer working principle and main factors affecting achievable resolution. In the second part, Michael will present a bunch of sample measurement data and application examples that focus on the resolution of EDS peak overlaps and nicely illustrate the benefits of a high-resolution spectrometer. So let me start right away with an overview of the QUANTAX WDS system. The system is a full-featured spectrometry system which comprises basically three main components shown here. These are namely the XN spectrometer, which is a so-called parallel beam spectrometer, an SVE6 signal processing unit, which powers the spectrometer hardware and is responsible for the pulse processing and data exchange with workstation computer running our SPRI2 software as the third component. With SPRI2, it's possible to operate all our EDS, WDS, EBSD, and microXRF devices from a single user interface, making QUANTAX WDS an integral part of the entire QUANTAX family of devices for SEM-based microanalysis. Being a so-called parallel beam spectrometer, the fundamental working principle of the XN spectrometer is based on the presence of a so-called parallel beam optic, which is shown in the sketch on the right-hand side here. This optic transforms X-rays diverging from the sample into a highly collimated parallel beam, which propagates along the optical axis of the spectrometer. As the optic is positioned pretty close to the sample in the SEM chamber, it captures a large effective solid angle of up to roughly 150 millisteradian, which leads to a very high sensitivity and which constitutes the major advantage of such type of spectrometer over conventional roll and circle designs. Inside the spectrometer, the parallel beam then strikes one of the flat analyzing crystals where Bragg diffraction occurs. This means that only photons of a certain energy fulfilling the Bragg condition are allowed to reflect towards the proportional counter, which is finally used for X-ray detection. According to the Bragg equation, the energy, or wavelength lambda, of these photons is a function of the adjustable Bragg angle theta, which is the incidence angle of the beam relative to the crystal surface, and the lattice constant d of the analyzing crystal. Basically, this setup describes an X-ray monochromator, which is very narrowband and hence capable of delivering high spectral resolution. Since spectral resolution is the main topic of this webinar, I'd like to go a bit more into the details here. So the spectral or energy resolution of an X-ray spectrometer is usually defined via the width at half maximum height of an elemental line peak. And there are basically two things that determine this width. The first one is the natural line width of the X-ray line, which is related to the lifetime of the excitation state responsible for the X-ray emission, and which follow energy X-ray lines are in the range between roughly 0.2 and 3 electron volts. The second determining factor in peak broadening is peak broadening caused by the spectrometer itself, which simply means that with a real-world spectrometer, we will never end up with the red curve shown in the plots here, but rather with something like the blue curve, which is shown in the second graph, and which is a broadened version of the red curve. Peak broadening occurs likewise in EDS and WDS, but has completely different origins and differs substantially in magnitude, with WDS being the clear winner in this regard. In a WDS, peak broadening is mainly due to photons not impinging on the analyzing crystal surface at one sharply defined Bragg angle, but rather at a somewhat broadened distribution of Bragg angles. One reason for this are imperfections of the analyzing crystal or multilayer structure, like crystal defects, waviness of B-layer boundaries in a multilayer, etc. Another one is an imperfect parallelization of the beam due to aberrations of the parallel beam optic, or misalignment between optic and the sample in the SEM. Now, in order to minimize broadening due to parallelization errors, we did two things. First of all, we equipped the X-ray spectrometer with a so-called grazing incidence optic. This is a mirror optic which is, apart from its size, very similar to optics used in large X-ray telescopes, and which produces a highly collimated parallel beam of low divergence, and hence leads to less peak broadening as, for instance, polycapillary-based optics do. The second point is that we mounted the optic to a 3-axis motorized positioning unit, which, together with the easy-to-use auto-optic alignment function implemented in the Esprit software, enables accurate alignment of the optic with respect to the sample under study, and hence eliminates beam parallelization errors due to the mismatch between excitation spot on the sample and focus point of the optic. The unique combination of a grazing incidence optic with its high optical performance and an auto-alignment feature results in an outstanding performance of the spectrometer, which is demonstrated, for instance, by the plot here on the right-hand side, showing the silicon K-alpha peak at an outstanding resolution of 3 electron volts. Due to dispersion of the detector's crystal material, electronic noise and incomplete charge collection effects, peak broadening is much more pronounced in SED-based EDS than in WDS. Especially in the low energy X-ray range, where the line density is highest, the limited resolving power of EDS frequently leads to peak overlaps, preventing proper analysis of a sample with EDS alone. In such more demanding cases, the X-ray spectrometer, with resolutions being typically in the 4 to 20 electron volt range, can reveal much finer details from the overlap regions and hence act as an ideal complement to EDS. To illustrate this, Michael will now present lots of nice WDS energy scans which were mainly acquired on fairly standard materials, but which cover a wide range of common EDS peak overlaps. Michael, please go ahead.
Thank you, Jörg, and hello, everybody. High spectral resolution. That should go on here. Next slide. Okay. High spectral resolution or high energy resolution is one of the primary arguments for deployment of WDS in X-ray microanalysis. The limited spectral resolution of EDS frequently causes serious peak overlap problems, which are listed here in this table. or at least there are the most prominent examples listed. The list may be much longer. As you can see, peak overlaps concern all fields of scientific and industrial X-ray microanalysis applications, including biological, geological, and material science examples. In the following, we present typical examples from various natural and synthetic materials where the superior spectral resolution provided by the QUANTAX WDS is evident and facilitates exact and reproducible determination and quantification of the respective elements. The first two application examples are sulfides, because most sulfides have elemental peaks that directly overlap with the sulfur K-alpha peak in EDS spectra. All spectra shown here are combined EDS and WDS spectra. You can see this here. This is in the background, the broad spectrum. This is a section of the EDS spectrum. And in the foreground with slightly darker colors, you see the WDS spectrum, which is much better resolving. And this WDS spectrum is acquired sequentially by scanning across the energy ranges. Please remember that the WDS measures a single energy or wavelength at a time. Galena in this example. Galena is a sulfide mineral of the composition PBS, and due to its high lead content of about 87 weight%, galena is the most important lead ore which has already been used in ancient times. Here in the present slide we can see that the lead M series peaks overlap with the sulfur K-alpha peak in EDS spectra. The result is a broadened peak with a hump on the right, on the high energy side. You see this hump here, and this is the broad EDS peak. The sulfur K-alpha and the lead M lines cannot be resolved by EDS. In contrast to that, WDS clearly separates the individual peaks of sulfur and lead in the corresponding spectrum. Molybdenite is a sulfide mineral of the composition MOS2 that forms aggregates of platy hexagonal crystals. Besides graphite, molybdenite is the most important mineral for the production of mineral lubricants for technical purposes. For molybdenite, the overlap between the L series peaks of molybdenum and the sulfur K-alpha peak is even more pronounced than the elemental peak overlap for galena. The result is that only a broadened peak with a tail towards the high energy end can be seen with EDS. So this is the EDS peak in the background. You see this peak with a tail to the right side. But in contrast to that, the WDS spectrum separates the individual peaks of both elements. We can see the lines for, or the peaks for molybdenum and sulfur separately. Monazite is a rare earth thorium phosphate with some minor contents of yttrium. Primarily, it is an accessory mineral in granites and gneisses, but it considerably accumulates in placer deposits. Monazite is an important ore for the rare earth elements, especially for lanthanum and cerium. And it is also a major ore for thorium. Scientifically, the mineral is important for geochronology, that means for dating of rocks and geological processes, due to its content of the radioactive element thorium that decays over time and records the processes. X-ray peak overlaps concern multiple rare earth element L lines and M lines, but also the minor yttrium L peaks beside the major phosphorus K-alpha peak. You can see here the dominant K-alpha phosphorus peak and the minor yttrium peak, which completely disappear within the EDS spectrum. The energy difference between phosphorus K-alpha and yttrium L-alpha is fairly large, with 92 electron volts. However, the low amount of yttrium and the resulting small X-ray peak because of these low peaks, the yttrium will nevertheless be ignored by the EDS, since the small peaks disappear in the tailing of the dominant phosphorus K-alpha peak. Now we get to a transition from geosciences to material sciences, since this zirconia is man-made. Cubic zirconia is basically zirconium dioxide, and it is a popular synthetic gemstone used as an economic substitute for diamonds in jewelry. Calcium oxide with 5 to 8 weight%, or yttrium oxide with 15 to 18 weight% are often added for stabilization of the zirconium dioxide crystals. Moreover, other elements such as hafnium may also be present in minor amounts. The EDS spectrum of a cubic zirconia shows a broadened irregular zirconium L peak, but the contribution of other elemental lines cannot be distinguished easily. The WDS spectrum, in contrast, clearly resolves the X-ray lines of zirconium and yttrium, and even detects hafnium reliably based on its M-series energy lines. Here you see the lines of yttrium in red, and in blue the multiple lines for zirconium, and here some minor lines or minor peaks for the hafnium, which can be quantified then by WDS. High spectral resolution may also be important for glass analysis. Glasses primarily consist of silicon dioxide, commonly with considerable additions of aluminum oxide or calcium and sodium oxide. Other elements, such as transition metals, are added in minor amounts during the production of glass in order to amend its properties, the properties such as color, refraction index, density, and so on. Small amplitude peaks from minor and trace elements that are close in energy, close to each other in energy, such as sodium K-alpha at 1040 electron volts and zinc L-alpha at 1012 electron volts. They are both indicated here, green sodium and blue zinc. They cannot be resolved by EDS. We just see this broad peak, which is just slightly above the background. However, these peaks can be resolved by WDS. The WDS spectra show two distinct peaks with a relatively high peak background ratio. And the last example here for material sciences is on semiconductors. Tantalum silicide is an inorganic compound of the group of silicides. It is used as a contact material in microelectronics. Furthermore, it also finds use in microelectromechanical systems and for oxidation or temperature-resistant coatings. Tantalum silicide and also tungsten silicide, which is somewhat comparable, they also occur as refractory phases in semiconductor materials such as silicon wafers. To achieve a high spatial resolution during quality control of these wafers, the analysis have to be carried out at low acceleration voltages, complicating the identification of these phases. Since only the energy lines of the M series are generated at low excitation energies, which overlap with the substrate silicon K-alpha line, the resulting EDS peaks are slightly broadened and mask the presence of the refractory phases. Only by using WDS elements such as tantalum and tungsten are identified without any doubt. Here is a summary of the EDS and WDS properties with respect to resolution. spectral resolution of both techniques, EDS and WDS, is given via the full width of the elemental line peak measured at half maximum height, the FWHM value. And you can see these values here for EDS in this column and for WDS in this column. The FWHM for EDS is in the range of 70 to 90 electron volts for the X-ray lines of the preceding examples. And it increases hereby towards higher photon energies. So like 91 for lead, the highest photon energy side. The FWHM value for WDS is an order of magnitude smaller than that of EDS, as you can see here. So with that, we get a much better resolution. However, there's a way to help EDS, and that's deconvolution. Deconvolution is really a nice tool. Deconvolution is also called peak stripping. It is a mathematical procedure of peak fitting and peak subtraction from an area of peak overlap in the spectrum, taking into account physically constant ratios of X-ray lines of an element's peak family. In many cases, this method is very helpful to expose the peak overlap in EDS spectra and estimate the likely element ratio by least squares approximation. However, in cases of extreme overlap, or in cases where elements are present in low concentrations, this numerical aid may not be successful. In the present figure, we see a broad EDS peak in gray here, and this is the EDS peak of the actual sample. And the sample is tungsten silicide in this case. And in this energy position, we have a strong overlap of the silica K alpha and the silica K alpha line, which would be here, and the tungsten M alpha and the tungsten M beta lines. Tungsten M alpha, tungsten M beta. The deconvolution recalculates the overlap and hence numerically separates silicon in orange here from tungsten in magenta. Here in this slide, we see the WDS spectrum of the same sample, tungsten silicide. And this figure clearly shows a distinct physical resolution of the silicon and tungsten peaks, with a half width being approximately 20 times improved when compared to those of the pure element EDS peaks. So with this example, I think it gets clear that in some cases where deconvolution is not successful, WDS is the ultimate choice. Its superior spectral resolution results in significantly higher peak-to-background ratios and better spectral dispersion, and thereby minimizes the possibility of peak overlaps. So far we saw qualitative results. Now let's get to quantitative results. Here's a table with some quantitative data. The present table shows that during quantification, WDS resolution is superior to EDS deconvolution. This is especially relevant for elements without further lines available for the deconvolution algorithm than those in the overlapping peak only. During analysis at low acceleration voltages, like in this example here with 5 kilovolts, deconvolution uncertainties may affect many more compounds than at high acceleration voltages, since high energy X-ray lines of the elements of interest are not excited at these low kVs. In the present case here for molybdenum sulfide, it's the molybdenum K alpha line at 17 kilo electron volts that cannot be excited and be included in the deconvolution model. And for the second example with tungsten silicide, it's the tungsten L alpha line at 8.4 kiloelectron volts, which is not excited at this present acceleration voltage. High spectral resolution is also useful during mapping. This slide here shows the combined EDS and WDS map. Sulfur was measured by WDS and lead was simultaneously mapped by EDS. And the slide shows an element distribution map for lead here, lead M alpha line and sulfur K alpha, acquired on a sample from a rechargeable battery. Herein, lead identifies the areas composed of lead dioxide, and so the bases here are surrounding, and sulfur defines the areas where remnants of lead sulfate deposits are present from the reaction with the sulfuric acid. Let's sum it all up. What we learned from today's seminar, today's webinar. Sorry. Jörg introduced the Bruker QUANTAX parallel beam WDS on SEM. He has nicely shown that the X-Sense WDS facilitates high spectral resolution analysis. Applications with the need of high spectral resolution include biological, geological, and material sciences and industries. We have shown that deconvolution methods cannot fully replace true spectral resolution. High spectral resolution is important for qualitative and quantitative analysis as well as mapping. And with this, I think it is obvious that QUANTAX WDS is a powerful tool for scientific and industrial applications. Thank you very much.
So with this, thanks to Jörg and Michael for their excellent presentations. We'll now have the question and answer session, which will last about 15 minutes. We'll see how many questions we have. First, a quick reminder to everybody, you can still submit questions by entering them into the Q&A field on the right-hand side of your screen and pressing the submit button. So if you have questions, please go ahead. Meanwhile, we already had a couple of questions, and so let me have a quick look. So here the first question was, what are typical beam currents required for such a WDS measurement? And so I think Jörg is going to answer that one, so I'm going to hand over to Jörg again.
Well, this is, yeah, of course, a good question, which is not so easy to answer since it really depends on the application or the type of application. Maybe let me put it this way. So in cases of light element analysis, typically very low beam currents in the range of some nanoamperes or nanoamps are sufficient, simply due to the outstanding sensitivity of the spectrometer. While on the other hand, applications which involve measurements at higher energies where the sensitivity of the spectrometer falls off, higher beam currents will be required, of course. So maybe generally we say that an SEM should be, for a reasonable combination with an SEM should be that the SEM should be capable of producing at least 20 nanoamps at 30 kV accelerating voltage as a minimum requirement. At least this is what we need for completing the installation of such a spectrometer, which includes a very extensive energy calibration within a reasonable amount of time. And apart from that, it's simply that the higher the beam current capabilities of the SEM are, the more flexibility the user has regarding different applications. Maybe that's the bottom line, yeah.
Okay, I see here there's a question for sample preparation. Yeah, samples for WDS analysis have to be prepared well, so at least for quantitative analysis, since you're comparing your results of your sample with the standard, so they have to be in the same state as your standards. So good polishing is required for good quantitative data. For just qualitative data, you can afford a certain roughness of your sample, so some micrometers of roughness. So like you saw in the mapping, for example, this was just qualitative data, and obviously the surface was rough, and it was still possible to map the rough surface. But for good quantitative data, you need a well-polished surface of your sample. And the next thing is about coating. Non-conductive material has to be carbon-coated, and it should be coated with the same thickness as your standard. If you don't have, or if you're using conductive samples, like for example metals, you don't need to coat them, but your standard has to be the same uncoated. So because you're comparing your intensity, X-ray intensities with the standard, you have to be sure that your standard and your sample are in the same condition. And okay. So you don't need coating either when you're working in low vacuum, because it's also possible to use the X-Sense WDS at low vacuum. This is, I think, an advantage. A microprobe with WDS could never work at low vacuum. It's always working at high vacuum, but the WDS on SEM, at least the X-Sense, can work at low vacuum as well.
So Michael, there's another question. Are powders okay, or do we need a flat surface?
Yeah, yeah, that's in addition to what I said before. We saw the map with a rough surface. It's okay to map it qualitatively, just to show where the elements are. You will get some shadowing effects, but at least you see the distribution of your sulfur or lead in that case. So qualitatively, it's okay to map a rough surface, or to see in your spectrum if the element is there. But for quantitation, it's quantitative measurements, it's not okay. So a powder could be measured qualitatively, but not well quantified.
So there's another question was that last SEM image, a pseudo-colored image, or an X-ray map overlaid on a micrograph. Michael, could you answer this as well? You acquired this data. I believe it's an SEM image with a map overlaid, right?
Yeah. So yeah, this is. We could switch back to the image. Yeah, it was this one here. Yeah, it was the SE image of the SEM. So it's indicated that. Do I have the oh. Okay. So it's indicated here, the SE image. This is the background is showing the topography of your sample, and the overlay is with the element composition. The concentration of sulfur is measured by WDX. Here it's held in green colors, and the lead was simultaneously measured by EDS. So, and this is an overlaid image with the SE image and the compositional images.
Okay, so there's a next question.
Yeah.
Would WDS help separation of strontium and silicon
Yeah, indeed, this is possible, but it depends on the concentration also, but resolution of these peaks is possible. I already did some test measurements for this strontium contents in feldspar. This is often interesting for some studies, and some normal concentrations of strontium, like a few or several hundreds to thousands ppm of strontium next to a high silica peak is an easy task. It is possible to determine that and quantify that.
So the next question that I may answer is, what is the maximum scattering angle at crystal analyzer allowed by the spectrometer setup? So although I'm not 100% sure whether I understand this question correctly, I think it relates to the Bragg angle range accessible by the spectrometer, and this is 12 degrees up to 70 degrees, which opens up, or which basically defines the energy range is covered by the individual analyzing crystals, which in total are 6 different crystals, multi-layers in the spectrometer. So we have, in the spectrometer, we have 4 different multi-layers for the very low energies, starting with a 200 angstrom multi-layer for the very low energy end, starting at roughly 70 electron volts, up to, let's say, the boron K alpha line, and an 80, 60, and 30 angstrom multi-layer for increasingly higher energy ranges. And this is, and apart from that, we have, which are pretty common crystals in WDS, we have a TAP and a PET crystal for the higher energies. But of course, the Bragg angle ranges, this is set by the mechanics of the spectrometer, and this is identical for all the crystals, 12 to 70 degrees. Yeah.
There's a question for the detection limits. Yeah, it's like in a microprobe, detection limits are in the range of hundreds of ppm. In the best cases, maybe several tens of ppm. It depends on the line or on the element that you are measuring, but it's somewhat in that order of a few hundred ppm. So you have to remember that you're always measuring a very small volume, so 100 ppm is really great.
So we have another very interesting question. It's a bit lengthy. Using S4 Explorer, we have recorded chemical shifts for several inner shell transitions, like the K alpha of aluminum and aluminum nitride or aluminum oxide. Could you see chemical shifts with the present setup? That's interesting. Yeah. The point here is, I would say in principle yes, but not the preparation, but the handling of the sample is a bit tricky then. The point here is that typically when you put in a new sample in your SEM, you want to perform a WDS measurement. First of all, you're going to perform this optical alignment, and you have to know that by means of the optical alignment, basically what you do is to bring an elemental line to its correct position on the energy scale by adjusting also the vertical position of the optic. That means by changing the position of the optic, the peaks you see can be shifted a bit to the left, to the right on the energy axis. So if you now have different compounds with different chemistry for one element, and prior to each measurement of these compounds, you do an individual optical alignment, you will see all the peaks at the same position on the energy scale. So you will not be able to see any chemical shifts. But this can be, this effect can be circumvented basically if you put all your samples onto one sample holder at the same height, perform the optical alignment only once, and then perform all the measurements successively. Then you should see peak shifts due to chemical changes. And we saw such shifts like for boron, for instance, which is a very typical case. We have not looked, so far as I know, into aluminum, but would be interesting to have a closer look there.
I see a question here for mapping again. How long does it take for WDS mapping? So, well, there's not a single answer. It depends. So I would say mapping takes 10 minutes to several hours. It actually, the actual time depends on the intensity of the X-ray line that you are measuring. So this intensity depends on the element you're interested in and on its concentration within the sample. So yeah, for light elements, for example, you get high intensities, and you're done within a few minutes. Like I saw it once with the carbon mapping on carbon and steel, two phases steel with different carbon contents, and it was fine to get, or I got a nice map within 10 minutes, and further mapping was not worth it since I deposited a lot of carbon on the sample afterwards. So that's quick done, and other elements, trace elements of transition metals, for example, it would take a long time to get a good result, probably. But this is comparable to microprobes. It's the same, like on the microprobe. The only difference is that you have a single spectrometer, not 4 or 5 spectrometers like on the microprobe. And mapping can be done in a scanning mode with the SEM. So depending on the peak and the size of the image or the area that you want to map. So in a small area you can use beam scanning for mapping, and in that case WDS mapping is as fast as EDS mapping. When you're using stage mapping, you're driving the stage, then the mechanical reaction time will lead to much more time for mapping.
So there's just another question coming in. Michael, this is again for you, since it relates to the, I believe, to the map you showed. How can you tell if there are lead O2 or lead O4 by WDS?
Yeah, this needs then some quantitative mapping. So this is possible also when in the present case I didn't use standards for the mapping, but it's you could quantify your map, and then you would see the relative amounts of lead and oxygen to distinguish between lead dioxide and lead with higher oxides amounts. So it was more PbO and PbO2.
Yeah, so thank you for all your good questions here. We are coming to an end here now. So I once again want to say thanks to Jörg and Michael for the presentations, as well as for the nice discussion here in the end. Just as a reminder, today's event has been recorded and will be available on demand for viewing very soon. And with that, I would like to thank you all for being here with us today, and we hope to have you with us again at future webinars here. So yeah, everybody, thanks a lot and have a good day.